Let us now evaluate integrals that involve hyperbolic functions. Hyperbolic functions such as hyperbolic sine, hyperbolic cosine, hyperbolic tangent, hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. But we need to have a rundown first of the formulas. So for integrals that involve hyperbolic functions, we have the integral of hyperbolic sine u du equal to hyperbolic cosine of u. The integral of hyperbolic cosine is hyperbolic sine. The integral of hyperbolic tangent u du is ln of hyperbolic cosine of u. The integral of hyperbolic cotangent u is ln of the absolute value of hyperbolic sine of u. The integral of hyperbolic secant u du is arctangent of hyperbolic sine u. The integral of hyperbolic cosecant u du is ln of the hyperbolic tangent of u all over 2. The integral of hyperbolic secant squared is hyperbolic tangent. The integral of hyperbolic cosecant squared u du is negative hyperbolic cotangent of u. The integral of hyperbolic secant u hyperbolic tangent u du is negative hyperbolic secant u. And finally, the integral of hyperbolic cosecant u hyperbolic cotangent u du is negative hyperbolic cosecant u plus c. Notice that all these formulas are very similar to those integrals that involve the trigonometric functions, no? Except for hyperbolic secant and hyperbolic cosecant. No? For hyperbolic sine, it is positive hyperbolic cosine of u plus c. Before, the integral of sine u du is negative. Now, for hyperbolic function, the integral of hyperbolic sine is positive hyperbolic cosine. Another is the integral of hyperbolic tangent u du, which is ln of the hyperbolic cosine of u. Involving the tangent function, the integral of tangent is negative ln of cosine u. So for the hyperbolic function, it is positive ln of hyperbolic cosine u. And finally, before, the integral of secant u tangent u is positive secant u. But for hyperbolic functions, the integral of hyperbolic secant u hyperbolic tangent u du is negative hyperbolic secant u plus c. Okay? So as before, we need to memorize all these formulas and we must know how to apply them correctly. As before, we have to identify the function u and then check on the differential. Okay? Let us have some examples. Let us evaluate the integral of hyperbolic sine of 3 over y dy over y squared. So it is of the form hyperbolic sine of u. Alright? That means that our u is 3 over y and du is negative 3 over y squared dy. So the missing term here is negative 3. So hyperbolic sine of 3 over y, negative 3 over y squared dy, negative 1/3. And the integral of hyperbolic sine is hyperbolic cosine. So our answer is negative 1/3 hyperbolic cosine of 3 over y plus c. Next, we evaluate the integral of dt all over hyperbolic cosine squared of 40. Now what we do here in our integrand is to take the reciprocal of hyperbolic cosine, which is hyperbolic secant squared 40 dt. So now it is of the form hyperbolic secant squared u du, where our u is 4t and our du is 4 dt. So we shall be writing 1/4, and then the integral of hyperbolic secant squared is hyperbolic cotangent of 40 plus c. For our third example, let us evaluate the integral of hyperbolic secant of square root of t, hyperbolic tangent of square root of t, dt over the square root of t. So immediately we can recognize that our integrand is of the form hyperbolic secant u, hyperbolic tangent u du. So our u is square root of t, and since this is equal to t to the 1/2, our du is 1 over 2 square root of t dt. So we shall complete our du. We will write hyperbolic secant of square root of t, hyperbolic tangent of square root of t, dt over square root of t, but we know that it lacks 1/2, so we multiply it by the reciprocal 2. And the integral of hyperbolic secant hyperbolic tangent is negative hyperbolic secant of u, which is square root of t plus c, or negative 2 hyperbolic secant of square root of t plus c. Let us take on another one. We evaluate the integral of hyperbolic cosine squared x over hyperbolic sine of x dx. Alright? We cannot use here the power formula because sine, hyperbolic sine, is in the denominator. If it were in the numerator, if it were hyperbolic cosine squared x, hyperbolic sine x dx, then you can apply here the power formula. Okay? But since hyperbolic sine x appears in the denominator, let us think of a way on how to evaluate the integral. So for this particular integrand, especially for hyperbolic cosine squared x, we apply an identity. Now for trigonometric function, we have sine squared theta plus cosine squared theta equal to 1. But for hyperbolic functions, the corresponding identity is hyperbolic cosine squared x minus hyperbolic sine squared x equal to 1. So we make use of this identity. We shall now write hyperbolic cosine squared as 1 plus hyperbolic sine squared x all over hyperbolic sine of x dx. And what do we do next? No? We shall split this into 2. 1 over hyperbolic sine, which we know is equal to hyperbolic cosine of x. And the other integral is hyperbolic sine squared over hyperbolic sine, which is equivalent to hyperbolic sine of x dx. Right? So for the first integral, we have, it is of the form hyperbolic cosecant u du. Right? And for hyperbolic cosecant u du, the integral is ln of the absolute value of hyperbolic tangent of u over 2 or x over 2. And the integral of hyperbolic sine of x dx is, as we all know, is equal to hyperbolic cosine of x plus c. Okay? Let us evaluate the integral of 4 plus hyperbolic secant of 5c all over hyperbolic cotangent of 5c dc. What we do is we split this again into two. 4 over hyperbolic cotangent is the same as 4 hyperbolic tangent of 5c plus, we do the same thing, hyperbolic secant of 5c, and then the reciprocal of cotangent or hyperbolic cotangent is hyperbolic tangent of 5c dc. Alright? So we write the constant 4, then hyperbolic tangent of 5c dc. We need 5 to complete the differential, so we introduce 1/5. Let us do the same thing for the second integral. Hyperbolic secant 5c, hyperbolic tangent 5c dc. It also lacks the constant 5, so we multiply it by the reciprocal. So for the first integral, it is 4 times 1/5 or 4/5. And we know that the integral of hyperbolic tangent is ln of hyperbolic cosine of 5c. And then we know that the integral of hyperbolic secant hyperbolic tangent is negative hyperbolic secant. So that becomes negative 1/5 hyperbolic secant of 5c plus the constant c. We take on another one. Say we have x squared times, or let me write hyperbolic cosecant x cubed times the quantity hyperbolic cotangent x cubed plus 1. Okay. So we shall now write this as, let us distribute x squared hyperbolic cosecant x cubed. So that is x squared hyperbolic cosecant x cubed hyperbolic tangent x cubed dx. Okay, plus x squared hyperbolic cosecant x cubed dx. For the first one, it is of the form hyperbolic cosecant u hyperbolic cotangent u du. So our u here is x cubed and du is 3x squared dx. So we need 3 that will be equivalent to 1/3, and the integral of hyperbolic cosecant hyperbolic cotangent is negative hyperbolic cosecant of x cubed. For the second integral, it is of the form hyperbolic cosecant of u. Again, we have the same u and du. So we shall be needing 1/3. And the integral of hyperbolic cosecant is ln of the absolute value of hyperbolic tangent of u, which is x cubed over 2 plus c. Okay, so that is our final answer. Let's have some more. So the integral hyperbolic tangent of 4x hyperbolic secant squared 4x dx. For this integral, we'll not be using any of the formulas we had, no? 1 to 10 formulas involving hyperbolic functions. Why? Because what we will apply here is actually the power formula, where your u is hyperbolic tangent of 4x and your du is hyperbolic secant squared 4x times 4 dx. So our integral is actually of the form u raised to 1 du, except for the missing constant 4. So our answer here will be 1/4, and then the power formula applied to our integral will give us hyperbolic tangent squared of 4x all over 2 plus c. Or equivalently, that is 1/8 hyperbolic tangent of 4x plus c. So in this case, even if our integrand involves the hyperbolic functions tangent and secant, we did not use any of the 10 formulas we had earlier. No? Instead, we applied the power formula because that is the appropriate formula for such kind of integral. Okay, so let us evaluate another one. We have the quantity 1 plus hyperbolic cosine 2x multiplied to the quantity 1 plus hyperbolic tangent 2x dx. So let us multiply these two. We'll be getting 1 plus hyperbolic cosine 2x plus hyperbolic tangent 2x plus hyperbolic cosine 2x hyperbolic tangent 2x quantity dx. So let us integrate them one by one. We start with the integral of dx, which is x, then plus the integral of hyperbolic cosine 2x is 1/2 hyperbolic sine of 2x. Then the integral of hyperbolic tangent 2x dx is 1/2 ln of the ln of hyperbolic cosine of 2x plus, now in here, hyperbolic tangent 2x is equivalent to hyperbolic sine over hyperbolic cosine. So notice that hyperbolic cosine 2x can be cancelled, and what remains is hyperbolic sine of 2x, and its integral is 1/2 of hyperbolic cosine 2x plus c. Okay? Let us have two more examples. Say we're given the integral of 4 plus hyperbolic secant of 3h quantity squared dh. So we know what to do with this. Because of the exponent 2, we can just expand, and it will give us 16 plus 8 hyperbolic secant 3h plus hyperbolic secant squared 3h quantity dh. So we integrate term by term, beginning with 16dh, that will be equal to 16h plus 8 plus 8. The integral of hyperbolic secant is equal to what? arctangent of hyperbolic sine of u. But because of 3h, that will be 8 all over 3. Alright? And that is arctangent of hyperbolic sine of 3h. Alright? Plus, we know the integral of hyperbolic secant squared u, which is hyperbolic tangent. But we check our u, which is 3h, so that will be 1/3, and hyperbolic tangent of 3h plus c. Right? And finally, let us work on the integral of hyperbolic sine of 2y over the square root of hyperbolic cosine of 2y dy. Okay, notice here that we have a power of hyperbolic cosine together with hyperbolic sine. And we know that the derivative of hyperbolic cosine is hyperbolic sine. So just like the other example we had earlier, what we will use here is the power formula. We can write this as hyperbolic cosine raised to negative 1/2 of 2y, hyperbolic sine of 2y dy, where our u is hyperbolic cosine 2y and du is 2 hyperbolic sine 2y dy. So clearly, this is of the form u to the negative 1/2 du. We only have to introduce the constant 2 and 1/2. So we'll get our answer 1/2, and then the integral of u to the negative 1/2 is used to the positive 1/2. But our u is hyperbolic cosine of 2y. Raised to 1/2 over 1/2 plus c. So we can cancel, of course, 1/2. And our final answer will be the square root of hyperbolic cosine of 2y plus c. Okay? So, you work on the following integrals. You evaluate the integral of 3 minus hyperbolic cosecant of 5x squared dx, the integral of y dy over hyperbolic sine of y squared, and hyperbolic cosecant squared 2x plus hyperbolic cosecant 2x minus 3 all over hyperbolic tangent of 2x dx. So work on this, and then I'll be back after 15 minutes.